Hello everyone. In this lecture, we'll solve the rest of the tutorial questions. This is question number 5. The question is calculate the noise spectrum and total noise power generated in a low pass filter with R equal to 1K and C equal to 1 picofarad. Yeah. So first we'll try to understand the question. The question is to calculate the noise spectrum and total noise power generated. So if you would have listened the previous lectures, you would have noticed about two things what we have learned. One is power spectral density, either SIF or SV of F, which is power spectral density, which we call it as power spectral density. And second one is average power. Average power we have written it as IN square bar or Vn square bar. Even you would have noticed the units of this. This one, power spectral density, is volt square per hertz or ampere square per hertz, and this is actually volt square or ampere square. Now, in this problem, the question is calculate the noise spectrum. So when I say noise spectrum, spectrum can be obtained only from spectral density, power spectral density. So if you can get SV of F or SI of F, from that definitely you can draw the spectrum. So for basically to find spectrum, what you should find is power spectral density first, so that we know how to find power spectral density. Now the second is total noise power generated. We know how to find noise power. Noise power is again obtained from this Vn square or In square formula. So if you have noise power, to find the total power, what you can do is you can integrate the noise over the range of frequency from 0 to infinity. So these two things you should know first, then we can proceed to this particular question. Now in order to find the noise spectrum, so what we are expecting here is the noise spectrum. So basically it is output noise spectrum. So here we can so when we start this problem, or I think I'll do it over here. Yeah. So this is question number 5 tutorial. Fifth question from tutorial. Yeah. So if you this is the circuit diagram which is given with a resistor and capacitor, and this is the output. Now to find the noise spectrum, what we told is we should find the power spectral density, or we should find the output power spectral density. Now from the first lecture of noise, we know how to write the output spectral density, that is written as input noise spectral density multiplied by H of F square, mode square. So this is the formula what we have. Now if you look at the components in the circuit, one is a capacitor. We'll assume that it is noiseless, assuming it is ideal. Now you have a resistor R, and that is having some noise source, and we will represent that as a voltage source in series, and this is actually the noise component there. So from this so a resistor is the component which produces noise, and that noise we have included here as the noise at the input. So directly I can write SVI of F, which is the input noise. Input noise is nothing but the noise provided, noise from the resistor. So it can be written as 4 kT into R. Now H of F. H of F is actually the transfer function of this RC network. So if you have an R and C, to find the transfer function you mark here VI of S and VO output O of S, R and C. If you write output expression VO of S, it is actually VI of S into 1 by SC divided by R plus 1 by SC, or you can write V naught of S by Vi of S as 1 by 1 plus SRC, which is nothing but the transfer function of this low pass filter. Now when I express that in terms of F here, what I can write is, it is 1 by 1 plus S can be written as J 2 pi F R into C. Now what is the magnitude of this H of F? Magnitude is 1 by under root of 1 plus 2 pi FRC the whole square. Now what we need is square. Yeah, so now if I write SV of F, SV of F can be written as SV of F is equal to this is the formula. So SVI of S is 4 kT into R multiplied by magnitude of H of the whole square, it is 1 by 1 plus 2 pi FRC the whole square. This is SV naught of F. This can be further written as 4 kT R into 1 by 1 plus 4 pi square F square R square and C square, which is your SV naught of F, or this is actually a noise spectrum. This is a noise spectrum. This is actually a pass spectral density. And how you can get the noise spectrum, or how you can plot the noise spectrum, is basically when your F is equal to 0, the spectrum is actually at can plot it as, when F is equal to 0, the value is 4 kT into R, and as F increases, or say at a particular value of F equal to 1 by 2 pi RC, where F is equal to 1 by 2 pi RC, the entire term becomes 1 by 2, so it is 2 kT into R. So this is having a low pass response, and this value is actually 2 kT into R. This is the noise spectrum. This is the first part of the question is to calculate the noise spectrum, so that is done. Yeah. Now the second part of the question is to find the total noise power. Total noise power. So we know the noise power is given as, noise power is actually Vn square bar, which is given as the pass spectral density multiplied by the unit hertz bandwidth. Now to find the total noise power, what you can do is, total noise power can be obtained by integrating your pass spectral density, which we obtained in the previous, it is 4 kTr by 1 plus 4 pi square F square R square C square into df. So if we integrate the power spectral density, yeah, this integration you can do, and if you do the integration properly, you will get the answer as kT by C. So you can use the integration formula. I'll write a square by s square plus a square. Integral of this is actually 1 by a tan inverse x by a. Please try this to solve this, and you will get that the total noise power is kT by C. So the question was to find the noise spectrum which we obtained, and the total noise power generated, that also we obtained. Now what you can do here is, you can substitute the values to find the total noise power. K is actually Boltzmann constant at room temperature T, and the capacitance value to obtain the kT by C noise. So that is your fifth question. Now if you look at the sixth question, sixth question is, calculate the maximum noise voltage that can be generated by a single MOSFET. So So this is the MOSFET, and calculate the maximum noise voltage that can be generated from a single MOSFET. So what we are the question is to find Vn square out bar maximum. So to find the maximum output noise voltage, I can write this as In square bar, which is the noise current multiplied by R out square, and when your R out is maximum, your noise voltage is also maximum. And now to get maximum output resistance, so the maximum resistance of a MOSFET is actually R0, and how to obtain R0 is, if I load this transistor with an ideal current source, in this case my output resistance is R0 parallel to infinity, which is R0, which is the maximum resistance that can be obtained from a single MOSFET. That in turn will give you a maximum noise voltage. So your R out max is basically R0, and your In square bar, assuming MOSFET in saturation, is 8 kT by 3 into Gm. So the answer is 8 kT by 3 into Gm into R0 square. So that is your maximum noise voltage generated by a single MOSFET. Next question. The question is, for an NMOS current source, calculate the total thermal and 1 by f noise. 1 by f noise is your flicker noise in the drain current for a band from 1K to 1 MHz. So in this band you should find the total current, flicker as well as thermal. So first we'll write thermal noise, which is given as 8 by 3 kT Gm ampere square. To find the total thermal noise, we should integrate over the band. So total thermal noise, to get total thermal noise, this multiplied by delta F. So this is the basic formula from your spectral density. Now to obtain total noise, this delta F will be rewritten as, or in place of delta F, what we can write is, you can write 1 megahertz minus 1 kilohertz, that is the band. So this is approximately equal to 8 by 3 kT Gm into 10 power 6 ampere square. That is the first part. Now the second part is to find the total 1 by f noise. So again 1 by f noise can be written as K. Now this, K is your flicker noise coefficient, K by WLCox into 1 by f into Gm square. Because we modeled flicker noise as a voltage component, now it can be written as current by multiplying with Gm square, or this can be written as K Gm square divided by WLCox and integrate from 1K to 1 meg 1 by f df, where this part is, if you do this integration, you will get this as ln of 10 cube, and your final answer as 6.91 the K value Gm square by WL into Cox. So please look at these three questions, question number 5, 6 and 7 carefully after watching the lectures on resistor as well as MOSFET noise, and practice it. Thank you.